Have you ever found yourself maybe just gazing up at the night sky and wondering about all the things we can't see? The vast hidden parts of our universe that remain a mystery. Welcome back to the Deep Dive. We're the show that cuts through the noise to get you the insights you need. Today, we're tackling one of the biggest puzzles in cosmology: dark matter. It's this huge invisible scaffolding holding everything together, but, well, it's incredibly elusive. Now, if you follow this stuff, you know the basics. But our mission today is a bit more specific. We're diving into a really crucial distinction, one that honestly gets misunderstood all the time. It's the difference between dark plasma and what some people call ordinary plasma in dark mode. We've got some great research here, including a paper called Dark Matter. Plasma is not ordinary plasma in dark mode, and that's going to be our main guide. Okay, let's unpack this. Our goal is simple: give you a shortcut to being properly clued in on this super cool, but yeah, often confusing little corner where cosmology and plasma physics meet.
That's right. And it's the critical, we get this clear, it's fascinating how just one term, dark plasma, can cause so much confusion if we don't understand the physics underneath. And look, this isn't just about words, about semantics. It really impacts how we read astronomical data, how we even think about experiments. Ultimately, it shapes our whole picture of the universe. So yeah, our mission: define true dark plasma, show how it's not just ordinary plasma that's gone dim, and explain why mixing them up is a real problem for understanding dark matter.
It's subtle, but absolutely vital.
Absolutely vital. It's like thinking a power outage means the furniture disappeared.
Right.
It's still there, just not lit up.
Ooh.
So to set the stage, let's start with what we do know. Before we get into the really dark stuff, what is ordinary plasma? Let's get a baseline. Good place to start. Okay, ordinary plasma. Fundamentally, it's an ionized gas, fourth state of matter. Solid, liquid, gas, then plasma. It's everywhere. It makes up something like 99% of all the visible stuff in the universe. And it's made of particles we know well: electrons, protons, other ions. Standard model stuff. Crucially, these particles have electric charge. That means they interact, and strongly, with the electromagnetic force. Light, magnetism, electricity. You see it in stars, the gas between galaxies, lightning, even the aurora. It's common stuff, cosmically speaking.
Okay, so it's common, it's energetic, it interacts with light, but you mentioned this idea of ordinary plasma in dark mode. That's where the wires get crossed, isn't it? What does it mean for ordinary plasma to seem dark? Does it just switch off?
No, not at all. And that's exactly the misconception. When ordinary plasma is in a dark mode, or maybe better put, a low emissivity state, it just means it isn't emitting much visible light. Think of a campfire ember after the flames die down, or maybe a neon sign that's off. It's not glowing brightly, but the gas is still there. The plasma hasn't vanished. Its fundamental nature hasn't changed one bit. Still made of those standard electromagnetically interacting particles. So no, it doesn't become truly invisible, just very, very faint in the wavelengths our eyes happen to see.
That makes sense. My first thought might be, well, if it's not glowing, it's undetectable. But the research clearly says that's wrong. So if ordinary plasma goes into this dark mode, it's not visibly bright. How do scientists still find it? What are the tricks?
It's a great question. And it really shows how sophisticated astrophysics has become. Because even in that low emissivity state, ordinary plasma is, well, it's far from silent observationally. Think of it like this. Even if it's not shining visibly, it leaves other fingerprints.
Yeah.
All across the electromagnetic spectrum. We just need the right instruments.
Different kinds of light.
Exactly. We use, for instance, infrared and ultraviolet spectroscopy. So molecules vibrating or rotating, or electrons jumping between specific energy levels in atoms like in nitrogen or oxygen, argon. Common stuff that give off light, just not visible light. It's like listening for a specific radio frequency instead of looking for a light bulb. Our eyes can't see it, but our instruments pick it up loud and clear.
Okay, IR and UV. What else?
Then there are X-rays and radio waves. Powerful telescopes looking at these wavelengths can spot even weakly ionized plasma. There are specific processes like Bremsstrahlung, that's radiation from electrons slowing down as they pass atoms.
Right.
Or synchrotron radiation from electrons spiraling in magnetic field. These are things you expect from any plasma, bright or dim. And we see these signals routinely, from planetary atmospheres, huge nebulae, even the halos around galaxies. So this idea of dark mode ordinary plasma being truly invisible, it's just wrong. It's spectroscopically active, accessible to our instruments, just maybe not shining in the narrow band of visible light. It's not hiding. It's just speaking a different language, wavelength-wise.
Speaking a different language. I like that. And just to be super clear for everyone listening, I remember reading, sometimes people call things like sunspots solar dark plasma, but that's just ordinary stuff too, right? Just cooler or something, not related to this dark matter puzzle.
Precisely. Sunspots are a perfect example of ordinary plasma that appears darker. But it's absolutely standard matter, just cooler, denser, with strong magnetic fields messing with things. We can see sunspots across many wavelengths. They're definitely not related to the cosmic dark matter we're trying to understand today. Good clarification.
Okay, great. So we've firmly established what dark mode ordinary plasma is and isn't. Now, let's pivot. Let's talk about the real mystery guest. True dark plasma. This is a completely different category, right? What is it made of? Why is it so fundamentally different?
Indeed. Now we're stepping into, well, hypothetical territory, but it's profoundly important. Dark plasma, unlike ordinary plasma, is thought to be made of dark sector particles.
Dark sector particles.
Yes. These aren't our familiar electrons, protons, ions. We're talking about entirely new particles, things not in our standard model, things we haven't directly discovered yet. And here's the absolute key difference. These dark sector particles theoretically do not interact with the electromagnetic force at all. Zero electromagnetic interaction, which means they don't interact with light. Photons just pass right through them, or rather, they don't see each other. Instead, the hypothesis is they might interact through a separate force, maybe a dark electromagnetism, a whole different gauge interaction that only works within the dark sector.
Wow.
Like a parallel set of rules operating alongside ours, but completely separate electromagnetically.
So it's not just dim, it's genuinely invisible across the entire electromagnetic spectrum.
Yeah.
No radio waves, no X-rays, nothing. It doesn't emit, absorb, or scatter any photons we know of.
Exactly that.
Yeah.
Genuinely invisible. No electromagnetic footprint whatsoever. So how do we know it's there?
Yeah.
Or how do we infer it might be there? Solely through gravity. If you connect this to the bigger picture, that's how we infer dark matter in general exists. We can't see it, but we see its gravitational pull on the things we can see.
Right, like gravitational lensing.
Precisely. Gravitational lensing, where light from distant galaxies gets bent by massive, unseen stuff in front. The amount of bending tells us there's way more mass than we can account for with visible matter.
In galaxy rotation curves, too.
Exactly. Galaxies spin too fast. The stars on the outer edges are moving much quicker than they should if only the visible stars and gas were providing the gravity. Something massive and invisible must be there, forming a huge halo, providing the extra gravitational glue.
Okay, so gravity points to something massive and invisible.
Yes. But this raises a critical question, doesn't it? If we only see its gravity, how can we be absolutely sure it's this new dark plasma or dark matter, and not just some extremely well-hidden form of ordinary plasma that we've somehow missed electromagnetically?
That's a fantastic question. And I think this is where the cosmic microwave background comes in, right? The CMB, that baby picture of the universe. How does that ancient light settle the argument? How does it help us definitively tell these two dark ideas apart?
Ah, the CMB. Yes, it's
Yeah.
incredibly powerful. It is our baby picture, a snapshot from when the universe was just about 380,000 years old, a tiny fraction of its current age. Before that time, the universe was this hot, dense soup of plasma, totally opaque. Light couldn't travel freely. But as it expanded and cooled, protons and electrons combined formed neutral hydrogen, and suddenly, poof, the universe became transparent. The light from that exact moment has been traveling ever since, and that's what we see as the CMB. And it gives us these incredibly precise constraints on what the early universe was made of and what conditions were like.
Okay, so how does it rule out ordinary plasma?
Well, here's the kicker. If those huge structures we now see gravitationally, the ones causing lensing, holding galaxies together, if they were made of ordinary plasma, even plasma in dark mode, they would have interacted with the light in that early hot soup. Remember, ordinary plasma interacts electromagnetically. That interaction would have left very specific signatures, specific patterns in the tiny temperature fluctuations, the anisotropies we see in the CMB today. Think of it like sound waves sloshing through that early soup. Ordinary matter would affect how those waves propagated and how they imprinted on the light.
And do we see those signatures?
We absolutely do not.
Yeah.
Our measurements, especially for missions like WMAP and Planck, are incredibly precise. They show a pattern, but it's a pattern that conspicuously lacks the specific imprints ordinary plasma would have created if it made up all that missing mass.
Wow. So the absence of a signal is the key.
Exactly. In stark contrast, dark matter, including hypothetical dark plasma, doesn't interact electromagnetically. It's gravitationally active, sure, but it just sort of flowed through that early plasma soup without really interacting with the light particles, the photons. It didn't leave those electromagnetic fingerprints on the CMB. Its non-interaction is perfectly consistent with the CMB pattern we observe. It's fascinating, isn't it? How sometimes the most powerful evidence in science is what you don't see. It tells a very clear story about what wasn't the dominant player electromagnetically back then.
That really does sound like the ultimate cosmic lie detector test. But was there ever a point where scientists thought maybe, just maybe, there was some wiggle room? Could some exotic, ordinary plasma still explain things? Was that ever seriously debated?
Oh, that's a really sharp question. And yes, absolutely. In the earlier days, before we had the super high precision CMB data we have now, there were definitely alternative ideas explored. Could very, very faint ordinary plasma or maybe some exotic forms of baryonic matter we hadn't thought of account for at least some of the missing mass effects? People looked into it. But with each new generation of CMB observations, COB, then WMAP, then Planck's the error bars got smaller and smaller, the constraints tightened dramatically, the specific signatures predicted from any significant amount of electromagnetically interacting matter, like ordinary plasma, just became glaringly absent from the data.
So the data just kept pointing away from ordinary stuff.
Consistently, it pushed the possibility of ordinary plasma being the bulk of dark matter further and further into the margins, to the point where it's just not considered viable anymore to explain the cosmic scale gravitational effects we see. It's why non-baryonic dark matter, something fundamentally non-electromagnetic, remains the leading explanation by far. The CMB evidence is just that strong.
Okay, wow. That really clarifies the CMB's role. So let's boil this down. For anyone listening, why is getting this distinction right, ordinary plasma in dark mode versus true dark plasma, why is it absolutely critical? What does it mean for the big picture, for finding dark matter?
It's critical because confusing them sends us down completely wrong paths.
Yeah.
Imagine if we assumed all this gravitational evidence was just from ordinary plasma hiding really well. What would we do?
Yeah.
We'd build better telescopes to detect faint electromagnetic signals across more wavelengths,
Yeah,
right?
makes sense.
But if the answer is true dark plasma or some other form of dark matter that doesn't interact electromagnetically at all, then all those efforts looking for faint light would be, well, completely wasted. They wouldn't find anything because there's nothing electromagnetic to find.
Ah, okay, so it dictates the entire search strategy.
Entirely. This isn't just semantics. It's about fundamental physics and where we invest our time, our resources, our brain power. Let's recap the differences. Ordinary plasma, even dim dark mode plasma. Standard model particles, interacts via electromagnetism, detectable across non-visible EM wavelengths, would have left clear CMB imprints. True dark plasma, hypothetical dark sector particles, interacts via gravity, maybe a dark force, genuinely invisible electromagnetically, inferred only by gravity, leaves no EM trace in the CMB, which matches what we see.
Big difference.
Huge. So mixing them up doesn't just confuse the theory, it fundamentally misinterprets the universe and risks us missing the real nature of dark matter. If you think about the bigger picture, true dark plasma represents something, well, revolutionary. It challenges our whole observational approach and demands totally new physics beyond the standard model we know. It means looking for interactions we barely understand yet.
And just to head off another potential mix-up, you mentioned ambiplasma briefly in the notes, matter, antimatter plasma, also totally different, right?
Oh, completely different. Ambiplasma is fascinating, equal parts matter and antimatter plasma, but it's still made of ordinary particles and antiparticles. It interacts electromagnetically like crazy.
Yeah.
It's relevant for, say, high-energy physics or maybe exotic astrophysical environments, but it has absolutely nothing to do with the dark matter, dark plasma puzzle we're discussing. The core takeaway really is, ordinary plasma, no matter how quiet or dim, is still an electromagnetic player. True dark plasma, if it exists, plays by completely different non-electromagnetic rules.
What an absolutely fantastic deep dive. We've gone from the familiar glow of ordinary plasma to the truly deep unknown of the dark sector. It sounds simple, dark versus dark mode, but the difference is, well, cosmic. You've definitely given us all a massive shortcut to understanding this really critical point in astrophysics. We've seen how ordinary plasma, even when dim, is still detectable with the right tools because it plays the electromagnetic game. But true dark plasma, that's a whole other beast. Invisible electromagnetically revealed only by gravity and strongly supported by that CMB evidence. Seriously, thank you for making these really complex ideas so clear. So thinking about all this, what does it mean for you listening right now as you ponder the universe?
Well, this discussion, I think, really hammers home how much we don't know, how much is still out there to discover. It reminds us that our usual tools, the ones based on light and electromagnetism, they might only be showing us a tiny sliver of reality. The fact that something like dark plasma could exist, making up a huge chunk of the universe but being almost totally invisible to our current methods, that's humbling. It forces us to push the boundaries, to think about new physics, new ways of seeing. What does detection even mean if it's not electromagnetic? That's the frontier. And it raises a question for you to think about. If so much of the universe potentially operates outside the forces we know best, what other hidden realities, what other modes might be out there, waiting for us to invent entirely new senses, entirely new ways to perceive and study them? Maybe the next great discoveries won't come from telescopes at all.
That is a truly mind-bending thought to end on. A perfect place to pause. Keep exploring, keep asking those big questions, and we'll be right back here for another deep dive into fascinating topics next time.